In this video, we're going to talk about ambiguous context-free grammars in programming languages and what to do about them. We'll begin by looking at our favorite grammar for expressions over plus and times and identifiers. And we'll just look at the string ID times ID plus ID. Now it turns out that this particular string, and let's write it down one more time, ID times ID plus ID. This string has two parse trees using this grammar. Let's do the parse tree on the left first. We begin with the start symbol E, and the first production in this derivation that gives us this parse tree must be that E goes to E plus E. E plus E. And then we replace the leftmost E by E times E. We use the production E goes to E times E, and we still have the plus E left over. And at this point you can see that we're going to get this parse tree. We've done, with those two productions, we've done this much of the construction of the parse tree. And the rest of the productions are just generating these IDs. So that's 3 more productions, and we can see that if we do those, we'll get ID times ID plus ID, no problem. All right, so now let's switch and do the derivation on the right, or the parse tree on the right. So this begins also with E, but this time we use the production E goes to E times E first. Right, and now we're going to replace the rightmost E by E goes to E plus E. So we have E times E plus E. And now with those two productions, we've done this portion of the parse tree. And once again, with 3 more productions, we can get to ID times ID plus ID. So there you can see we've got 2 derivations that produce 2 distinct parse trees. And just to be completely clear about this, in this case we're getting 2 different parse trees. Each of these parse trees has many derivations. Each parse tree has a leftmost derivation, a rightmost derivation, and many other derivations. This situation is something different. Here we have 2 derivations that yield completely different parse trees. And that is the sign or the definition of an ambiguous grammar. So a grammar is ambiguous if it has more than 1 parse tree for some string. And another way of saying the same thing is that there is more than 1 rightmost or leftmost derivation for some string. So if some string has 2 rightmost derivations or more, or 2 leftmost derivations or more, then that string will have 2 distinct parse trees, and that grammar will be ambiguous. Now, ambiguity is bad. If you have multiple parse trees for some program, then that essentially means that you're leaving it up to the compiler to pick which of those 2 possible interpretations of the program you want it to generate code for. And that's not a good idea. We don't like to have ambiguity in our programming languages and leave decisions about what the program means up to the compiler. Now, there are several ways to eliminate ambiguity from a grammar. And the most direct method, which we'll talk about first, is just to rewrite the grammar so it's unambiguous. That is, to write a new grammar that generates the same language as the old grammar, but only has a single parse tree for each string. So here's a rewrite of the grammar we've been looking at. And let's write down our favorite input string one more time, ID times ID plus ID. And let's look at how that string will be parsed according to this new grammar. So we begin with the start symbol E. And now notice that E can no longer generate a plus or a times. In fact, we've separated the grammar now into 2 sets of productions, 2 non-terminals. And E controls the generation of plus, and E prime controls the generation of multiplications. Okay? And so in order to generate a plus, we have to use the production E prime plus E. There's no other way to do it. And now if we look at E prime, what can E prime do? Well, E prime can generate an identifier times something, and if you look at the grammar, that is the only production that can generate an identifier times something else. The only other possibility involving times is to generate a parenthesized expression, which clearly won't match the string that we're trying to parse. So we have to use this production, ID times E prime. Well, now, in order to match the string, we can see that this E prime, the one remaining E prime here, has to go to ID. Because sandwiched in between the times and the plus is a single ID, there's only one production that will do that. So that's completely unique and determined. And finally, we have the last E over here, which we want to use to produce an ID. Well, how can we do that? Well, the E can go to E prime. In fact, it has to. And then the E prime can go to ID by itself. And there, we've managed to parse the string. So in general, what is this grammar doing? Well, as we said, we've stratified the grammar. We've divided the productions into two classes, one that handles plus and one that handles times, and there's one non-terminal for each operator. So the E productions control the generation of plus. And let's just look at what happens with that. So if E can go to E prime plus E, and then just sticking with the E productions, what can happen to this E here? Well, we could do it again. E prime plus E prime plus E. And if we do it one more time, we'll have E prime plus E prime plus E prime plus E. And in general, I think you see the pattern. We can generate any number of E primes summed together. And finally, that trailing E, there's always one E left at the end. Eventually that E, when we want to stop generating pluses, has to be rewritten to E prime. So in the end, we'll get a sequence of pluses, of E primes separated by pluses. Okay, and that's what E prime can do. I'm sorry, that's what E can do. Now let's look at what E prime can do. So E prime, and let's just focus on the first two productions, because we can see that the first two productions are handling identifiers times something, and then the last two productions are handling parenthesized expressions, but I hope you see the symmetry. That it's really the same idea for identifiers and parenthesized expressions. So we'll just do identifiers just to keep the slide from getting too crowded. So E prime can go to ID times E prime. Well, we can repeat that. We can go to ID times ID times E prime. And we can repeat that again. And I hope you're beginning to see the same pattern. This is the same idea as with plus. And what we wind up with then is a bunch of identifiers multiplied together, right? Because that trailing E prime in this case, in the end, can be rewritten to ID. Now, in the case of E prime, there are actually two alternatives. We could either be generating IDs or we could be generating parenthesized expressions. So really, for each of these IDs, it could have been a parenthesized expression. So let me just write some parenthesized E's down here just to remind us that we had an alternative. And in the end, we wind up with, a string of identifiers or parenthesized expressions separated by times. Okay? All right. So I hope you see how this works. There's the way that the grammar is set up, because we have these two separate groups of productions, all the pluses must be generated before any of the times. The times are going to be nested more deeply inside the parse tree than the pluses. The pluses are generated at the outermost level, and then the E primes will generate the times inside the pluses. And so the grammar enforces that times is going to bind more tightly than plus. The last detail that's worth pointing out here is that notice inside of the parenthesized expressions we have an E, not an E prime. And why is that? Well, once we're inside of a parenthesized expression, the whole purpose of parentheses is to show the explicit association, and so that we can have pluses inside of times by using parentheses. And that's all that's the significance of using E in this part of the grammar rather than E prime. To review, we started out with a grammar and a string we wanted to parse, ID times ID plus ID, but that grammar gave us two distinct parse trees for the string, and here are the two parse trees again. And by rewriting the grammar, we were able to eliminate this parse tree on the right. So this parse tree is no longer possible. The parse tree on the left is modified. There's more symbols in it now. I mean, for example, this became an E prime, and there was a chain here of non-terminals. This E went to E prime and went to ID, and there were some other minor changes in here. So the parse tree is not exactly the same as before, but we were able to get a parse where the times binds more tightly than the plus. So now let's consider another interesting example, if-then-else expressions where the else is optional. And here's one way to write that grammar. Here we have a if-then-else in the usual way, but then we also have a production where there is no else. So that's the case where the else is optional, and then maybe there are some other kinds of expressions. Now we don't need to concern ourselves with those, we'll just focus on the if-then-else piece. The problem is that this particular if-then-else expression has two possible parse trees. On the one hand, the else might belong to the outer if. That is, this particular inner if might have no else, and the else would be associated with the outer if. The other possibility is that the else belongs to the inner if, that we have this structure, if-then-else is nested inside of an if-then that has no else statement. And in what we want in every programming language I know of is the second form. We want else's to associate to the closest matching if-then, not one that's further away. We can write a grammar to express the desired association. The property we want is that every else should match the closest unmatched then. So whenever we see an else, we want it to be associated with the closest then that doesn't already have a closer matching else. So that means that the if statements are going to be divided into two categories. We'll have the matched ifs, those that have all of the then statements nested within them matched with an else, and the unmatched ifs, where some then expression inside of the unmatched if has no matching else. So what do matched ifs look like? Well, that's pretty straightforward. An if-then-else that's a matched if must have both a then and an else, and any nested if statements on both branches must also have matching else's. And if you have any other kind of a construct that's not an if-then-else, that's also considered a matched if. What about the unmatched ifs? One possibility is that it's simply an unmatched if, that there's no else. So we have an if and a then and no matching else out here. And now the crucial case, what if we have an if-then-else so that the top level if-then has a matching else, but that the unmatched if is somewhere inside? Well, then we claim that the unmatched if has to be in the else branch. It cannot be in the then branch. The then branch must be a matched if. And why is that? Well, think about it. If this was an unmatched if, that means that there would be some then in here that had no matching else. And then this else here would be closer to that then than it is to this then. And so it would have to match that one according to our definition. Okay, so that situation is not possible. So the only possibility for an unmatched if is that that is itself an if-then-else, is that the any if-then-elses on the then branch have to be matched, and the unmatched if-then-else has to be in the else branch. So now, reconsidering the expression we had before, we can see that this else is supposed to match this then. And so the association should be like this. And therefore, this parse tree on the right is not the one that we want, and the grammar that we gave on the previous slide will parse the expression according to this parse tree on the left. Now, you might think that the unambiguous if-then-else grammar is complicated and hard to understand, and frankly, I would have to agree with you. Unfortunately, it's impossible to automatically convert an ambiguous grammar to an unambiguous one. So we have to do these conversions by hand. If we're going to have unambiguous grammars, we have to figure out how to write them by hand, and that does result in significantly more complex grammars and grammars that are harder to read and maintain than if we use the more straightforward ambiguous grammars. A possibility is to try to somehow live with the ambiguity, because that would allow us more natural definitions. But then we would need some disambiguation mechanism. We need some way to tell which parse tree we want when more than one parse tree is possible. In fact, most practical parsing tools adopt this second approach. So instead of rewriting the grammar, we use the more natural ambiguous grammar, and the tool provides some kind of disambiguating declarations. The most popular form of disambiguating declarations are precedence and associativity declarations. So here is a natural grammar for plus over the integers, and this is ambiguous. Even just with a single infix operation, we can get ambiguity because this grammar doesn't tell us whether plus is left associative or right associative. And the simple solution here is to have an associativity declaration. So here we declare plus to be left associative, and this is the notation used in Bison. So Bison's a particular tool, and a %left plus declares that plus is a left associative operation, and so that would rule out this particular parse tree over here. Now here's a slightly more complex grammar, essentially the grammar we began with at the start of this video. Here we have plus and times over the integers, and again this grammar is ambiguous because it doesn't say what the precedence of times is with respect to plus. And the solution for this is to have multiple associativity declarations. We declare plus to be left associative, and we declare times to be left associative, and then the precedence between plus and times is given by the order. So the fact here that times appears after plus means that times has higher precedence than plus. Just one word of caution. These declarations are called associativity and precedence declarations, but that's not quite what's going on inside the parser. The parser doesn't really understand about associativity and precedence. Instead, these declarations tell it to make certain kinds of moves in certain situations. We won't really be able to explain this until we get much further into parsing technology, but just be aware that you have to be a little bit cautious in using these declarations. Usually they behave like associativity and precedence in the way you expect, but there are some situations in which they will cause surprising behavior, and it's important that you check the behavior of your grammar after you add these declarations.